1.3, the limit of a function. So we're going to be describing what happens at a specific point at a function as something approaches something. So to understand the limit, let's go over average velocity. I've explained this in my physics videos, but the average velocity of an object is how much meters it travels divided by seconds, where the meters are even, or where the distance is evenly split up to the seconds, because that's how division works. So the average velocity is how many meters per second something is traveling. I put per second on accident again. That would be acceleration, actually. So the average velocity is how many meters per second something travels, assumed at a constant velocity. And we say assumed at a constant velocity because let's say we throw a ball and it travels 30 meters in 5 seconds. That means it travels 6 meters per second, but not necessarily. We can know that parabolic trajectory slows down because the ball is going this way, and it would definitely be slower here than as opposed to here. So this just assumes that we're traveling 6 meters per second at any given point. And the logic behind that, there's no real logic behind that. That's just how we deal with average velocity mathematically. So what is I use that example, but we actually have a car example here. So take a car that travels 60 miles in 2 hours. That doesn't mean it traveled 30 miles in 1 hour. In fact, the first mile could have been 50 miles and the second 10 miles. So the average velocity formula, which is displacement over time, evenly splits the displacement over the time. Again, as we mentioned, I said distance before. That would be average speed, so that's a little bit different. But yeah, same concept there. And instantaneous velocity is slightly different. Now here we make sure that the 2 points are extremely close, because when we're looking at instantaneous velocity, we're looking at an instant in time. When you look at your speedometer, I might read 30 miles per hour. But how do you calculate that? Because if you're going at a certain speed, if we use the slope formula, which is actually the same thing as the rate of change formula, or how fast you are going at a specific instant in time, you realize that you can't divide by 0 if you've traveled. An instant moment of time would be using that as the final position minus the initial position. So that's the same thing as saying, if we start it here with this ball, we can't travel 0 seconds, because then the change in change in displacement over change in time, or displacement over time, would be 0 over how many meters traveled, which is impossible. This is indeterminate. So instead, we use 2 really close points to mimic that exact point of time, because this is probably going to be extremely accurate to how fast the ball was actually moving at that time, because then we can model, like, if that car was moving like 60 miles or 60 meters in like 0.5 seconds, then we can assume that, using some simple math, that he was traveling 120 meters per second, and that is very accurate, as opposed to if we dilute this and we go to like 120 meters per 4 seconds, then the longer the time gets, it's going to go more into average velocity. So that's the logic here. Intuitive definition of a limit is: a limit is the output as the input approaches a certain value. In mathematical terms, it's what f of x approaches when x approaches a, or that certain value. The formal definition is as x approaches a certain interval of a that is not actually at a itself. So we have this example here, and it's the limit as x approaches 2, x squared minus 16 over, I think, x plus 4. So let's use some algebraic manipulation here. This is the same thing as x minus 4, x plus 4, divided by x plus 4, cancel these out. Now we graph this, which is minus 4 right here, and then we draw the graph here. We draw the linear line going this way. Right, perfect. So limit as x approaches 2. So let's assume this is 2 here. So as you can see, as x approach, also there's a discontinuity at negative 4, which I should have mentioned. Because if you put negative 4 here, a denominator 0, and that's impossible. So negative 4 is somewhere around here. So if we scroll down here, there would be a discontinuity, like right there. But anyways, we're not dealing with that because we're dealing with the limit as x approaches 2. So we're not actually seeing what the point at 2 is. Instead, we can actually define 2 as something else. So 2 can actually be all the way up here, which is called a removable discontinuity. But it doesn't matter, because the right and left side are still approaching this area, or this point right here. So that's the logic behind the limit. So it's important to note, and I'm going to give you another example just so it's a little bit easier to understand. This notation means that you're approaching a from the right side. This notation means you're approaching a from the left side. So if we have a graph right here and a is right here, this is a plus, this is a minus, and we're seeing what they are. If they're the same value, which we'll denote as L, then there's a limit. However, if one differs, so if this is like 10 and this is 20, there's no limit. They have to be approaching the same value from both sides to be logically defining a both hand-sided limit. Okay, that was a little bit hard to say. So we'll do x squared minus 4, and then we'll do x minus 2. So this is the same as x minus 2 times x plus 2, and then we put these in parentheses so they become products of each other, and x minus 2. Cancel these out. Then we draw the graph x plus 2 this way, and we know that there's a discontinuity at positive 2, which is right here because you can't have 0 in the denominator. So that point is actually not defined here. So if you plug in 2, you'll get an indeterminate value. So if we approach 2 from the right side, guess what happens? We come over here, and let me think. Sorry. Wait a second. I'm looking. Something is off here. You can tell. Because I drew the graph right. Not too sure actually. Yeah, so x plus 2. So as it's approaching 2 from the right side, we see what it's approaching. And if we approach 2 from the left side, we'd see what it's approaching. So what's the issue here? X minus 2, x plus 2. X squared minus 2x, plus 2x. Yeah, this should be right. But then if you plug 2 back into this original equation, it's a little strange here. Well, let me redraw this graph just to make sure. So we're going to redraw this graph, and we cancel these out. So x plus 2, which only translates that upwards like that. So as x approaches 2 from the left side, it's somewhere around here, and if x approaches 2 from the right side, it's somewhere around here. That's the logic behind the limit there. And so x approaches 4 right here from the left side, and x approaches 4 right here from the right side. So that means there's a limit. So the notation would be limit as x approaches a would be of f of x, or yeah, of f of x equals 4, or L. And putting this in for our notation that we used here, x squared minus 4 is equal to 4, and that is your limit. So limit is what the output approaches as the input approaches a certain thing from both sides. Make sure that it's the same at both sides. Now this is the precise definition of a limit, and I hate this because it's slightly complicated. So I suck at explaining this, and this is usually where I mess up. So let's draw this Cartesian coordinate plane. I'm going to use very big things, so it's a little bit simpler to use. And here we'll use just a huge parabola. I'm not going to I'll just say it's x squared, although x squared is probably a little bit steeper. But so we know that the distance between 2 points on the x-axis, if this is a and this is x, it would be a minus x. Vice versa, it would be x minus a, which is the initial, or the final minus initial position. Now here's the twister, or the tricky part. Now, or it's not really tricky. You can also have negative displacement, using physics, I guess. So this is plus 2 traveled, but what if we swap these around, 4 and 2? Then if we use the formula in final minus initial position, we get negative 2. So did we travel negative 2? Theoretically, yes, but you can't travel a negative distance, or you can't go a negative distance. So what we do here is we actually absolute value it. So this is final initial position. And we absolute value it just to make it positive so that you can't have negative distances, or whatever it is. So now what we're going to do, and same thing for y, same concept. Let's say we want to take the limit, and let's just do 1, 2, 3, 4. So whatever. At 3, so let's take the limit as x approaches 3 of x squared. So that'll be somewhere around here. And now we're seeing what it equals from the left and right side. So first, it's important to note that for continuous polynomials, you can just direct substitution it because it's approaching the same value from the left and right side. For any continuous function, if x is within a continuous interval, if the limit is between the continuous interval. So how do I don't want to explain it in like calculus terms because it can be a little bit complicated. But if the limits, or if a, the value you're approaching, like right here, that 3 right here, if the limit is between a continuous interval, you can just direct substitute it in. And we'll get into squeeze theorem a little bit later. Actually, I'm not even gonna, actually, yeah, let me just write it down. You can direct sub, which just means that you can just plug in the value, just like a normal function. So right here, you could just plug it in. But the thing here we're talking about is the precise definition of it. And here they use epsilon and delta, but we'll be using C and D for simplicity's sake. So this is A. And this is A because that's what we're approaching. That's the limit we're trying to find at 3, but not at 3 itself, which is what the definition of this limit is. And we'll do A plus C, A minus C, because that's the distance formula, right? So, wait, let me think. Yes, so this distance would be C here, which is 1, and this distance would be C here, using these ticks. Now, what the theorem states, or the precise definition of a limit states, is that, as we know, the limit would be L here, or what it's approaching from both sides, but there has to be a ratio where a correspondent of L fits within or there has to be a real interval that matches the real interval of the input. So in other words, between this input of A minus C and A plus C, there has to be an interval where the outputs fall between, and this is the output right here. This is where the outputs fit. So L plus D would be corresponding to A minus C in the function output. But here, we'll do an example here just to make it a little bit simpler. So all it means is that within a given amount, or within a given distance from the limit's inputs, there has to be a given interval of a distance output, which is given by plus or minus D, or the distance between here. So this would be D, this would be D as well, and that would be the distance between those 2 points. Let me see how my book defines it actually. Well, it's actually right here, so let me explain. So if we define the limit of a function as x approaches A to be L, so the same notation we used here, we use epsilon and delta, but for sake of simplicity, I'll define them using C and D. So limit is actually at A, so that means x cannot be equal to A. So that's why we use the interval here, 0, x minus A, or here, the same thing as, so 0, x minus A, and then C, because x can't be at A itself, so it has to be a little bit bigger and a little bit below this ratio if we're finding the limit between these 2 bounds. Because if it's a little bit further from it, then it falls outside the possible range for it to be anywhere accurate to what A is actually approaching. And if it's too close, or if it's the same value, you can't do that because we're not finding the same value. Unless it's a continuous polynomial function, in which you could just direct substitution in. So if the limit is L, f of x minus L gives us the distance between the function's outputs and actually not 0, because the distance can be 0. Function's output and the limit. So for these 2 above, you must establish a link, or a suitable C for a suitable D. So for this interval right here, plus or minus D, there has to be an interval for the input, which is plus or minus C. So we'll use this example here, and I'm going to try not to mess up here, because this is usually where I mess up, and it's a little bit hard to prove. So let's come here, and let's prove that this is equal to this. So let's use the definition again. So for x, or sorry, the input. So 4x minus 5 minus, wait, sorry, 1 second. I gotta think. Give me 1 sec. Okay. I'm back. I just had to grab a book. So it would be x minus 3 has to be greater than 0, because x can't be at 3 itself. Otherwise, that would not be a limit definition anymore. And it has to be smaller than C, which is that suitable link. Or that suitable like plus or minus ratio, which is the interval that we'll check for the limit, which is the logic behind there. So same thing here, 4x minus 5, and we use absolute value again and we put the limit at the end because we're checking the distance between the function and the limit output. So guess what? This is the same thing as 4x minus 12. D, we'll factor out a 4 here, so it's going to be x minus 3 greater than d. So this is the same thing as x minus 3 is greater than d over 4 because we divide 4 on both sides. So same thing here. We can establish that x minus 3 is less than d over 4, which is the limit output. So for every c, there's a d over 4, that interval divided by 4. So that's the logic behind there. And that is calculus 1.3. So